Hello, my amazing math students. This is Mrs. A, and I love math. And tonight we're doing lesson 84 in your Saxon Orange Book. And we're talking about multiplication of radicals, and then we're going to talk more about functions. So remember that we can take the square root of 50 and we can split it up into the square root of 25 and the square root of 2. And we're going to repeat this rule in just a minute, but the square root of 25 is 5, so we can simplify square root of 50 to 5 times the square root of 2. Now the rule that we're using here is this one. The square root of m times the square root of n is equal to the square root of mn. Or we can say it as the product of the roots is equal to the root of the products. Pretty cool, huh? And here we have the root of the products is equal to the product of the roots. So we can go backwards on it. Okay, so any number that is under the radical must be greater than or equal to 0 in this textbook, because in this textbook we're only talking about real numbers. And if you have a negative underneath the radical, it is not a real number. We're going to deal with those numbers. And they are very much necessary in mathematics because the circuits that run your electricity have those types of numbers in them. They're called imaginary numbers, and we're going to deal with them in higher math classes. But in this math class, we're only dealing with real numbers. So that means that any number underneath the radical must be positive or 0. There are two examples for multiplying radicals. When we multiply radicals, we always multiply the rational parts, that means they're outside the radical, the rational parts together, and we multiply the irrational or the radical parts together. So 4 times 3 is 12, times square root of 3 times square root of 2 is square root of 6. Now square root of 6 cannot be broken down into anything that's going to simplify. So therefore our answer is 12 square root of 6. Final answer. Now let's look at example 2. We have 4 square root of 3 times 6 square root of 6. So now the 4 and the 6 being outside the radical are called rational numbers, and they're going to multiply together. And so we're going to have 24. Square root 3 times square root 6 is square root 18. Now 18 can be broken down. It is not a number that is in its simplest form. Could we pull out a perfect square out of 18? So anytime we're going to break it down, we always want to be able to find a perfect square if this is a square root. What if we take 24 square root of 9 square root of 2? Since square root of 9 times square root of 2 equals square root of 18, that is fine, isn't it? Okay, so the square root of 9 is 3 when it comes out of the radical. The square root of 2 cannot simplify any further, but this 3 multiplied by a 24 is going to give me a 72, and then I tack on the one that could not simplify, square root of 2. So let's repeat. The square root of 9 becomes a 3. The 3 times the 24 gives me 72 times the square root of 2. So get those down on your notes so that you will have them to refer to later on. So the answer here, I didn't circle it, was to the second example. Okay, so here we have 4 square root of 3 times 5 square root of 2, which is 20 square root of 6. Plus, now we're going to distribute over here. 4 times 6 is 24. Square root of 3 times square root of 3 is square root of 9. Now, this one we can't do anything about, but the square root of 9 is 3. 24 times 3 is 72. So we end up with 20 square root of 6 plus 72. These are kind of fun. Okay, so my cat is being kind of obnoxious outside the door. I'm sure you can probably hear him. We're going to multiply, this is example 4. We're going to multiply 4 squared of 2 times this parenthesis. So we're going to distribute here and then here. Now 4 times 3 is 12. Square root of 2 times square root of 2 is square root of 4, which we know is about to simplify to 2. Plus 4 times 5 is 20. Square root of 2 is just square root of 2. It's just multiplied by nothing. Over there it's a 1. Okay? So, if you don't have 1, you can think of it as the square root of 1. And here, this becomes a 2. 12 times 2 is 24. Plus 20 square root of 2, since this cannot simplify further. And we are ready to move on to functions. Now we're talking more about functions, and we can think of functions as a function machine. Okay, so here we have some inputs, 2, 4, and 7, that are going into our function machine. Inside our function machine will square the input and then add 5 to it and spit it out. So if we take 2 and we square it, that's 4, plus 5 is 9. If we take 4 and square it, that's 16 plus 5 is 21. If we take 7 and square it, that's 49 plus 5 is 54. Okay, so let's talk about terminology here. We can say that the image of 2 is 9. So the image is the y value that comes out. The output is 9 when the input is 2. Now we can say that with each one of these. The image of 4 is 21. The image of 7 is 54. The output is 21 when the input is 4, and the output is 54 when the input is 7. Now, you might think that we always have to have an equation like we did in that function machine to have a function, but that's not true. A function is any relation where every input has only one output. Now, those functions could be names of individuals and their ages. Okay, doesn't each person only have one age? So we could map a person to their age, and as long as the input is the person's name and the output is their age, then we would have a function, because every person, every individual can only be one age at any given time. However, if I flipped it around and let's say everybody in the classroom who is 12 stand up, then I may have more than one person stand up that is 12. That would likely not be a function. It would be a relation, though. A relation simply has one rule, that every input has an output. That's pretty easy. Now you notice this one down here, it's not even a relation. Every input, 4, 2, 1, does not have an output. So notice D is for domain, that's what X can be, that's what the input could be. R is for range, that's what the output can be, or the Y can be. So domain, range, domain, range, domain, range, domain, range. The input is the domain, whether it's a function or whether it's just a relation. And the output is the range, whether it's a function or whether it's just a relation. So a function is more specific than a relation. Okay, so all functions are also relations, but all relations are not functions. Okay, so here we have a function. Every x has a y and only one y. It does not matter that they have the same y. If I plug in 4, it's predictable. Out comes a 3. Remember what I said? Functions are predictable and functions are fair. If I plug in a 4, I know I'm going to get out a 3. It's not going to be a flip of the coin, is it? Okay, if I plug in a 2, I'm going to get out a 3. That is a function. If I plug in a 4, I'm going to get out a 3. If I plug in a 2, I'm going to get out a 5. If I plug in a 1, I'm going to get out a 6. It's predictable, and every input has only one output, so that is a function. This one is not a function, but it is a relation. A relation is a pairing. Every input has an output. Okay, so 4 might have an output of 3, or it might have an output of 5, so it's not a function. Okay, functions are always predictable. If I put in a 4, only one thing comes out. 4 to 5 to 3, or 4 to 5. 2 goes to 6. Okay, so the broken rule is right up here with the 4. 4 could go to 3, and 4 could go to 5. Therefore, this is not predictable, and it is not a function, but it is a relation. Every input has an output. Okay, now here, so we have a pairing. So 4 can go to 3, 4 can go to 5. Over here, we have a pairing, but no pairing for the bottom one. The 1 goes nowhere, therefore it is not even a relation. Sometimes we might just be given a bunch of ordered pairs. Now, can you tell me whether this set of ordered pairs is going to be a relation, or is it going to be more specific, a function? Okay, so every input is paired with an output, isn't it? So it is a relation. Now let's check and see if it is also a function. Does every input have only one output? Okay, 4, 3, 5, 7, 9, 3, 4, negative 5. Oops. 4 could go with 3, but 4 could also go with negative 5. That means 4 is not predictable. Okay, 4 can flop around like that. That is not a function. Okay, the rest of it's not a problem. Only the 4s are a problem. But if it breaks the rule one time, it's a rule breaker and it's not a function. Okay, so here, those are the points that we just looked at. This is a relation, but not a function. Well, what about this set of ordered pairs? Is it a function or just a relation? Okay, so here we have 4 and 4, and 4 goes to 3, and 4 goes to 3, and we have a 5, 9, 8, 6. Since 4 goes to 3 each time, they're just really restating that point again, aren't they? So that is a function. It just has the same point in there twice, which is fine. So here's the definition. A function is a mapping from each member of the input set, which we call the domain, to exactly one member of the output set, which we call the range. And we can always make ordered pairs out of the inputs and the outputs. And if we do make a list of ordered pairs, there will never be an input that has two different outputs. So if I have 4, 3 and 4, 5 as two different points, that is not a function because 4, the input, has 2 outputs. And that breaks the function rule. Okay, so here are 3 examples. We're going to look and see if each mapping is a function or just a relation. So here we have 4 goes to 7, 5 goes to 2, 6 goes to 14. Each one of our inputs has only one output. So we can say 14 is the image of 6, 2 is the image of 5, 7 is the image of 4, and yes, that would be a function because each input has one and only one output. What about this one? Okay, so Y goes to P, that's fine. A goes to X, and M goes to X. Now that's not a problem. M goes to X, A goes to X, M goes to X. The fact that 2 things go to 1 is not a problem. The problem is that M goes to X and 5. So one input has more than one output, therefore no, this example is not a function. What about this one? It's got some funny lines too. A goes to 5. 4 also goes to 5. 7 goes to 11. Does any input go to more than one output? And the answer is no. Okay, the fact that A and 4 both have 5 as an output is not a problem. Remember, it's a function if each input has exactly one output, and A has exactly one output, it is 5. 4 has exactly one output, it is 5. 7 has exactly one output, it is 11. So this one, yes, is a function. Now, let's think if we can come up with an easy way to figure it out. Okay, if we have a V shape going to the output, okay, so from the input to the output, if we have a V shape going from the input to the output that way, that is not a function. However, this one has a V shape going the other direction. It's going this way. That's not a problem. This one right here is going the other direction. So this one, the problem is right here. One input goes to two different outputs. This V right here, that little V shape, that's not a problem. Okay, so on the top, we have the set of real numbers is the domain. Any real number can go into this function. And then the little function machine here is going to take y equals x plus 2. So each input, x, which is part of the domain, is going to add 2, and then we get the output. So if we put in a 3, then out here we would get a 5. And if we put in a 7, then over here we would come out with a 9. Okay, but this is a function, right? Every input has only one output, because whatever it is, we're going to add 2 to it. And there's no way to get more than one answer, okay? So down here, we have two different sets. So if we're looking at this one right here, is it a function or is it not? 4, 6, 7, 2, 4, 5. And the answer is no, it's not a function, because 4 goes to 6, but 4 also goes to 5. Therefore, 4 is very unpredictable, and functions are predictable. Functions are fair. Okay, 4, 8, 15, 6, 11, 7. Notice that all of my inputs are unique. Therefore, there's no indication that one input goes to more than one output, and it is a function. So this one would be no, this one would be yes, and this one up here is a yes. Okay, so on this board we have 1, 2, 3, 4 problems that we're going to check each set of ordered pairs and see, are they a function or are they just a relation? Okay, so any set of ordered pairs is going to be a relation, isn't it? But each one of these sets we have to examine. Is there any first term input that has more than one output? If so, it will not be a function. So we have 1, 2, 2, 3, 3, 4, 4, 5. Now, a quick way to look at it is every input is unique. There is no repeated input. Therefore, it is safe to say that is a function. So this one is a yes. It is a function. What about this one? 1, 2, 2, 3, 1, 3, 4, 5. Okay, did you see it? 1, 2, 1, 3. The input 1 has two different outputs. Therefore, that is not a function. Okay, look at the next one. 4, 3, 2, 2, 4, 3, 3, 3. Okay, I have a 4 and a 4, but since they are both paired with 3, 4, 3, and 4, 3, that is just restating a point. That is not breaking the function rule, is it? The input 4 is paired with the output 5. One and only one output. So yes, this would be a function. 1, -1, 4, -1, -1, -1, 3, -2. It does not matter that 3 of them have the same y value. There is no repeated x value. Therefore, it is a function. Each input has one and only one output. Okay, it does not matter that they share an output. Each input has one and only one output. So this is a yes. So we had yes, no, yes, yes. Okay, take a look at those a little bit closer so that you can see them better. Okay, the last two problems, and we'll be ready to start our problem set, our practice set. So here we have 7 goes to 11, 6 goes to 4, 6 goes to 8. And what do you think? Is that a function or is that just a relation? It is just a relation because 6, an input, goes to 2 different outputs. Therefore, it is not a function. And here we have 6 going to 4, 7 going to 11, 5 goes nowhere. Remember, to be a relation, every input must have an output. This is not even a relation. It's definitely not a function. So it is neither. It is not a relation. It is not a function. And now we are ready to start our practice problems. Okay, the first two practice problems go back to our multiplying two radicals together. So copy these down on your boards and then pause your video and see if you can do them without me. And then come back and check and see how I do them. All right, so hopefully you did that. We're going to split the square root of 12. We're going to write down the 5. We're going to split the square root of 12 into the square root of 4, the square root of 3, times 4, the square root of 3. So now the 4 will multiply over here with the 5. 4 times 5 is 20. Times a 2. And then square root of 3 times square root of 3 is square root of 9. The square root of 9 is 3. So times 3. So 20 times 2 times 3. 20 times 2 is 40. 40 times 3 is 120. And 120 is the answer when you multiply these together. Now, another way you could do it, you could have left it like it is, and you could have said square root of 12 times square root of 3 is square root of 36, and the square root of 36 is 6. So 5 times 4 is 20, times 6 is 120. We didn't have to break this one down before we multiplied it. We could have just multiplied it at the beginning, maybe saved ourselves a little bit of time. Okay, so now down here we have 3 square root of 2, which we're going to distribute to 4 square root of 3. 3 times 4 is 12. Square root of 2 times square root of 3 is square root of 6, and there's nothing I can do to simplify square root of 6. Plus, now we're going to distribute over here. 3 times 5 is 15. Square root of 2 times square root of 6 is square root of 12. Now that's going to break down into square root of 4, square root of 3. So the square root of 4, so this breaks down to these two. The square root of 4 becomes a 2. So 2 times 15 is 30. So our final answer will be 12 square root of 6 plus 30. 2 times 15 is 30. Square root of 3. So this square root of 4 becomes a 2. 2 times 15 is 30, and we're left with 30 square root of 3 added to the 12 square root of 6. If you didn't get them right, write down what I did so that you can use them as an example for your homework problems. We are getting so close to being done here. So here we're telling whether each one is a function or not. So here we have A has an output of 5, 6 has an output of 11, 7 also has an output of 11, but 6 does not have two different outputs. and 7 does not have two different outputs. This is a function, isn't it? Yes. Gets a Y for yes. All right, so X goes to P. Y is an input. It goes to two different outputs. Therefore, no, this is not a function. Now, the next problem says, what is the domain of this one? And the other one says, what is the range of this one? Why don't we just do the domain and the range for both of them? So, the domain for this problem up here is A6, 7. So, if we were going to write the domain, we would write A, 6, 7. And then the range is 5, 11. So, we could say domain and then put A, 6, 7. And we could write it like a set. Okay? And range is 5, 11. Over here, the domain is X, Y. The range is P, A, 7. Pretty easy. Here is our last practice problem before you get to go do your homework. Okay, so we have 1, 2, 3, 4 separate sets of ordered pairs. And we're going to say, are they functions or are they not functions? We know each one of them are relations because each one is just ordered pairs. And every ordered pair has an input and an output. And that's all that is required of a relation. But are they also functions? Okay, 2, 1, 1, 2, 2, 2. What do you say? This is your practice problem. What do you think? Set A is not a function because 2 has an output of 1 and 2 also has an output of 2. So let's just put an X on that one. Okay? 1, 2, 1, 2, 2, 2. We do have a repeated X, but the X one has the same Y. So this is just a restatement of one point. Therefore, it is not breaking the function rule. And this one is a function because it just has a repeated point. 1 goes to 2 in both of those situations. 1, 2, 1, 3, 1, 4. That's a big no-no, isn't it? 1 goes to 2, 1 goes to 3, 1 goes to 4. 1 can't make up its mind. It's going to go just wherever it wants to. So no, that is not a function. 2, 1, 3, 1, 4, 1. Here they have the same Y value, but individual X values, it's okay if X's share a Y. But the same X cannot have more than one Y. Therefore, this is a function, and we have covered functions for this lesson. And have fun with your homework set. This is Mrs. A, and may God bless your day.